Hello, everyone. Welcome back. Today I'm going to be talking about vectors in two space and in three space. So, if you think about it, whenever we have some sort of line in two space or three space, we can also consider that a vector because a vector is just defined as anything with a magnitude and a direction. And a line in two space or a line in three space does have a magnitude and does have a direction, and therefore we can consider it a vector. And one key thing I want to mention is that OA is defined as the vector directed from the origin to any point A. So let me give you an example in two space here. Here it says draw the vector B for 3 on the xy plane. So here I'm going to start with my origin is right here, and then 4 over and 3 up is going to be my point B. And this vector is vector OB. And here it says note the x and y of point B4 over 3 are the components of the vector and are found at the tip of the vector, and the tail is at the origin, right? So we start at the origin, we go up to B for this vector. Good. Now, a plane, right, the two space plane is a theoretical wall, ceiling, floor, or some sort of flat surface. So, like, picture this as a floor, and we're just drawing this vector as a flat surface. Maybe this is a vector where a mouse is running across the floor in this direction and then, starts at the origin and then ends at point B. Or any other example you'd like to come up with for that, but basically they're on some flat surface and there's a movement like that. Now, what about three space? So, three space is a bit different. Three space is three-dimensional space, so it's not just a flat surface, right? It's not something flat. It's something that can, have three dimensions, right? We can be going in, you know, we can be going not just left or right, but also out and in, right? There's a third dimension there. We don't just have length and width, we also have height now. We have a third dimension now. Okay, and the way they've drawn the grid is supposed to make it look like there's a third dimension, right? This is a 3D object as opposed to a flat object in this case. So here it says to draw vector C3, 4, 5 on the XYZ plane. So the other one was pretty trivial. I'm sure for at least 10 years now, you've known how to plot a point on a graph, so that was probably pretty simple. This one might be a bit more confusing, and so I'm going to go over it in a bit more detail as to how we get 3, 4, 5. So 3 is with respect to x. So here's our origin. So 3 is over here, so I'm going to draw a point here. Now what about 4? 4 is y, that's the second one, so I'm going to draw a point here at 4. And then what about z is 5? So it's up 1, 2, 3, 4, 5. So notice how on these axes I just drew the points it was. So 3, 4, and 5. And now I need to connect the points together in order to form an object in 3 space that's going to have this vector. So I'm going to actually draw I was going to say a cube, but actually it'll be a rectangular prism because a cube would imply that all the sides are the same, and it would be, the three-dimensional version of a square, but this is not. This is a rectangle, or the three-dimensional version of a rectangle, I should say. Okay. I'm going to try to draw this picture as best I can. Okay, you know what? Actually, that came out pretty well. Good. So here's our point C, right? And so from here up to here is point C basically. And try not to look at this as a flat surface. Try to think of it as, it starts at the origin and it's coming out towards us, right? So partly it's going, a certain direction x and y wise, but also it's coming towards us. Don't forget that extra dimension, that z that's in here too, that wasn't there on the flat surface, right? Think of this like, oh, it's a box, and there's something that starts at one corner of the box and it goes up to the other corner of the box. Or maybe this is a room and there's a superhero at the origin, and then the superhero flies up to this corner and breaks right through, right? And we want to know just the vector of when it was in the box, right? Just that part of it, or the room, or whatever it is, right? So think of it definitely as, this is three-dimensional. There's three dimensions here. And just, you don't have to necessarily draw the box, but it makes it easier, I find, to figure out where the vector should go and get us to visualize it easier. So I like to do the box. I find it just makes it a lot simpler to understand. Okay, let's do another one here. This one says the points A, B, C, D, E, F, G, H create a rectangular prism in R3 where A of 0, 0, 0, B is 0, 5, 6, C is 4, 5, 0, D is 4, 0, 0, E is 406, F is 4, 5, 6, G is 0, 0, 6, H is 0, 5, 0. Plot the points on the XYZ plane below. So actually, the points are already drawn for us. We just need to label the points on this plane, and then we need to answer the question. So it said A was 0, 0, 0, so that's pretty easy. A, I'll do it in purple this time. A would just be this one, right? 0, 0, 0. B is 0, 5, 6. So 0 for X, and then we're going to go 5 over here this way, and then 6 in the Z direction. So we're going to get this one. So it's the same way we've always plotted points. It's just that there's a third dimension. So first number is X, second number is Y, and third one is Z. So this is B right here. What about C? C is 4, 5, 0. So it would be 4 in the X direction, and then 5 in the Y direction, and then nothing up, not up at all, right on the floor, because there's 0 for the Z direction for this one. So this is point C. Point D is 4, 0, 0. So that's just 4 over here for X. Then we have E, which is 406. So 4 in the X direction, nothing in the Y direction, and then 6 up in the Z direction. So this one would be E. Then we have F, which is 4, 5, 6. So 4 in the X direction, 5 in the Y direction, and then in the Z direction. This looks like this one isn't drawn exactly. It's hard to draw this one, but it would be like around there, let's say, but like, outwards, which will be more clear when I actually draw the box. So about there, we'll say that that's F. And then we have G is 0, 0, 6, so just 6 up in the Z direction, and that's it for G. And then H is 0, 5, 0, which maybe it's obvious to us that it's this one because it's the last one left, but also it only is 5 in the Y direction, and that's about it. So that also tells us we probably got them all right. So now I'm going to just draw a box here just to make it a little bit more clear and obvious to us what's going on. And I think this helps a lot of people to conceptualize the 3D-ness of this, right? Because at the end of the day, where you're just going to be drawing on a paper or an iPad or whatever, it's a flat surface, but we have to bring the 3D-ness to life. We have to believe that this is 3D because that's what we're representing here. Okay. So now there's some questions about what we just drew. The first one says, state the equation of ADCH. Okay, well, let's see. ADCH. Well, let's do that. So here we have ADCH. So it's right there. It's the same as point H, right? It is where Z is equal to 0. Okay, so there we have that one. Then we have EGAD. Okay, so let's try that one. E G A and D. So in this one, we would say y equals 0, right? And why is that? Let's explain why. Well, here we have y is 0 here, right? Here we have just the x. This is on the xz plane only. And this is the flat plane where there's no y, right? Whereas this last one here, the green one, was z equals 0 because in this plane, this is the plane where we have x's and y values, but we don't have any z values. It doesn't go up at all. Now, what about, I skipped B by mistake. Actually, let's do E first, and then we'll go to B. You'll see why in a second. Let's do B. So we have G BAH. So G, B, AH. So here we have this plane, and this is a plane where x is 0 throughout this plane. X is 0. Okay, now I'm going to actually get rid of those, and let's do some other things. Yeah, let's get rid of all that. But try not to get rid of anything we need. I got rid of a little bit of the F. There we go. That's a bit better. The next one, B, says GEFB. Okay, GEFB. So what's this plane? Well, let's look at it. This is the plane where Z is equal to 6, right? It's a plane where X and Y can equal lots of things. Z is equal to 6 because, if we look at it, it looks like this plane is parallel to this other plane here, right? This other plane of ADCH. It's parallel to this plane, right? This one's where Z equals 0, and then on the ceiling of our box, we have where Z is equal to 6 throughout there. So these planes, if they get expanded, will never touch, and hence they are parallel planes. Now, what about BFCH? Let's try that one. BFCH. So that's this one here. So if we look at this, it's like, okay, well, this is, this could be any X value and Z value we'd like. It has lots of different ones there. But with Y, it's just that slice where Y is always equal to 5. So I'm going to write that there. And likewise, this is parallel to the one where Y equals 0, right? This is just a different slice, a different slice of Y, so to speak, right? Because Y equals 0, if we recall, that was this one, right? So they're the same thing, just, they're parallel, right? Okay, amazing. All right, and then our next one is EFDC. So EFDC, like that, and this is just the plane with the equation x equals 4, right? X equals 4 throughout this whole plane, and this is parallel to the x equals 0 plane that we saw earlier. Good. All right. Awesome. Okay. So now it says, what plane, I guess I already answered some of these, but we'll go through them again. What plane is parallel to the XZ plane, but not the same plane? Well, the same plane as the XZ plane is where Y equals 0. So it would be this one, but it says not the same plane. So it would actually be this one here, BFCH. And this one asks, what plane is parallel to YZ, which the YZ plane is this one where X is 0. But not that one. So it would be this one here, EFDC. And then number 2 kind of asks us a bit of a bigger question. It asks us, well, what set of points that represent the rectangular prism A, B, C, D, E, F, G, H? So let's remind ourselves. Well, the thing is, we have we have different planes here that represent it, right? We have Z equals 0. It goes from Z equals 0 to Z equals to 6, right? So that's one of them. So Z can be anything from 0 to 6. What about Y? Y can be anything from 0 to 5. And what about Z? X. X can be anything from 0 to 4, right? Including those numbers. And so these are the sets of points, any combination, which there's going to be infinite, by the way, right? Because these are continuous variables, especially, right? Where we choose something for some value for X that's between 0 and 4 inclusive. Something for Y that's between 0 and 5 inclusive, and something for Z between 0 and 6 inclusive. Anything we choose, any of those infinite values we choose, will encompass this, will be within this box that we drew there, which is pretty interesting. All right, well, that is it for vectors in 3 space and 2 space. Next time, we'll be talking about a bit more detail of this. We'll talk about operations of the algebraic vectors in 2 space. And then we'll also be talking about operations of algebraic vectors in three space. There will be some examples of that in the future. Good work today, everyone, and we'll see you for the next one. Bye, everyone.